Okay, so we are going to do our next page of notes. This is called calorimetry. So what calorimetry is, it's the technique that we do in the lab to determine how much heat energy is in a substance. And so the way we do that is we mix two substances of different temperatures together and then measure how the temperature changes when they meet. So we need to make sure we understand that the law of conservation of energy says that energy cannot be created or destroyed. And so what that means in terms of kind of what we're looking at is that if something loses heat, then that amount of heat must be gained by something else. So there's always transfer of heat happening. It's not that like when ice cools down or heats up, that energy goes somewhere. It just doesn't disappear. So like when you are holding ice in your hand, you are losing heat from your hand. That's why your hand is feeling colder, and the ice is gaining that heat, causing it to go through that phase change into a liquid. So there's a relationship, and we talked about Q last time, but there's a relationship that compares how heat is lost from one thing and gained by another. And so when we worked out some of those Q equals MCAT questions, one of our Q's ended up with a negative sign on it. Well, that was telling us that heat was lost. And we talked about a few class periods ago that heat is always lost from the high to the low temperature. So if the hot stuff loses heat because it's transferring it to the cold stuff, we put a negative sign on it. And the law of conservation of energy tells us that if the hot stuff loses a certain amount of heat, well, then some cold stuff is going to gain that heat. And so the amount of heat that the hot stuff loses is equal to the amount of heat that the cold stuff gains. So those two things are equal to each other. So we can look at it as negative Q of the hot must equal positive Q of the cold when we're comparing two samples being mixed together. Another way to kind of look at this is negative MCAT of all hot has to equal positive MCAT of all the cold stuff. So that's a relationship between heat being transferred from something that's hot to something that's cold. And in the lab, the type of calorimetry that we use is called coffee cup calorimetry because it's easy and cheap, and an effective way for us to measure how heat energy or how much heat energy a substance has by transferring it. So I'm going to describe kind of this setup, this experiment, and then we'll actually do a lab exactly like what I'm describing. I'm going to draw some pictures here. So we first take a styrofoam coffee cup. So we just take a styrofoam coffee cup, but you actually take two of them and stack them together. So we got two styrofoam cups stacked together. And the reason we use styrofoam for this is because we're going to do an experiment inside of these cups, and we want to try and insulate the stuff going on inside of these cups from the environment that's outside of the cups. So we don't want the heat energy from the room, the air outside of the cups, to affect what's going on inside the cup. That's why we use styrofoam. So you have your two coffee cups stacked together, and then we put some water in here. So we got H2O in there. And we kind of take a couple measurements before we put the water in the cup. we have to take whatever measurements are necessary so that we know how much water is in the cup. And so the way you would do that is you take the mass of the empty cups and then you put your water in and take the mass of the cups with the water inside, and then you know the mass of just the water. The other thing we do is we plop a thermometer down in here. There's my thermometer. And we take the temperature of this water, and I'm going to call that the initial temperature because we are going to do something to cause this water temp to change. So we take the initial temp of the water. And meanwhile, while we got this thing going together, like this sucker's sitting on the lab table, it's just at room temp, hopefully. We take the mass and the initial temp of that water. We set up over here a beaker. So there's my beaker, and it's on a hot plate. And in here we have water, but this guy's boiling. So we got some boiling water over here. And we'll take the temperature of this boiling water, and it should boil somewhere really close to 100 degrees Celsius. But in this boiling water, we'll grab a test tube. And in the test tube, we'll put a little bit of metal. So I'll give you guys a sample of metal. And I won't tell you what the metal is because that's kind of the point of the lab. So in the test tube, there's going to be some unknown metal. You also need to know the mass of that unknown metal. So you just take the mass of that by putting it on the scale. And then we're going to take the initial temperature of this unknown metal, but we have to do that indirectly because it's not effective for us to stick a thermometer down into this test tube. So that is the reason we're taking the temperature of the boiling water, because we're making an assumption that if this metal is sitting in this boiling water for a period of time, that the temperature of this metal is the same as the boiling water around it. So if we measure the water, then we can assume that the temperature of the metal is the same. So we let the water sit in, we let the metal sit in this boiling water so that it can absorb all of that heat energy. So all this heat energy is going in. And then we take it and we quickly transfer it over into this cup. And the thing we would expect to happen is when you put the hot metal into the cold water, that we would see the temperature go up. And you would be right. It probably won't go up very much. But what you do is you measure what was that final temperature. How much did the temperature go up? So we also need to take a final temperature from after we add the metal. Now, keep in mind, this final temp, the metal and the water are both now in this cup. So the final temp is the same for both that metal and water because we've reached thermal equilibrium. So if it's the same, then the final temp is the same for both. And so if we come to the point where we have to calculate delta T, or the change in temp, the final temperature will be the same for both the water, which in this particular scenario that I described is the cold stuff, and the metal, which is the hot stuff. It's the stuff that's starting out hotter. So that is the lab that we're going to do. I'm going to give you some unknown samples of metal. You're going to do all this. You're going to take all those measurements. And then ultimately what I'm going to have you calculate is the specific heat for the metal. Because if we can calculate specific heat, then we can look at a chart to identify what the metal is. I will not tell you what the metal is. That would be your job. That's the reason we're doing the lab, is to figure out what that metal is. So let's do, I'm going to work out one example with you, and then I would like to see you work out this one on your own, and I will check that as an exit ticket next time I see you guys. So let's do this very first one. So since we got a couple different things going on, let me zoom in for us. We got a couple different things going on. We got hot stuff and we got cold stuff, which means we're going to have a lot of different variables. It's really important that you keep track of what goes where. So we're working with this relationship. Negative Q of hot has to equal positive Q of cold. Or the other way to look at that is negative MC delta T for the hot stuff must equal positive MC delta T for the cold stuff. So since I have all these variables, and since I have like an M on the left and an M on the right, I'm going to make myself kind of a table so that I don't get confused. So I make sure I put everything where it belongs. So I'll make myself a hot table and a cold column. So picking apart this question, I got to figure out what is hot and what is cold. So when you read through this, a piece of metal weighing 59.047 grams was heated to 100 degrees Celsius and then put into 100 milliliters of water, initially at 23.7 degrees Celsius. That first statement lets me know that my hot stuff, that's the metal. The metal is starting out hotter than the water. So in this case, the metal is hot, the water is cold. So let's pick apart what our masses are. They tell us straightforward what the mass of the metal is, 59.047 grams. And they tell us the volume of the water, and this is my mistake for not putting that information in here, but if you have milliliters of something and you want to know what its mass is, you got to use its density. The density of water is 1 gram per milliliter, so 100 milliliters of water is the same as having 100 grams of water. So the mass of our cold water is 100 grams. The next variable would be specific heat. If you kind of pick this apart, you get down here to the end, we find that we're looking for the specific heat of the metal. So that's the thing we don't know. The specific heat of water is always 4.18. They don't have to tell us that to know that that's the number we're going to use. It's always 4.18. And that's joules per grams degrees Celsius. The other thing we need to know is delta T, or how temperature changes. And this is where it gets just a bit tricky, and you got to be careful, because remember, delta T is T final minus T initial. So we have to do that for both of these things to figure out what the initial and the final temperatures are. So when we pick this apart, this says we take the metal and we heat it up to 100 degrees Celsius. That is the initial temperature of that hot metal, 100 degrees Celsius. And then it also tells us that the water is initially at 23.7 degrees Celsius. So kind of in my cold water column, I got 23.7 degrees Celsius for that water. It says the metal and water were allowed to come to an equilibrium temperature. That means an equal temperature. We just talked about how the final temperature has to be the same for both the metal and the water. And that equilibrium temperature is 27.8 degrees. So the final temperature for both of these is 27.8 degrees Celsius. And so now that's all we need to be able to determine our delta T. Final minus initial, final minus initial. This one is 4.1 degrees Celsius. This guy is 72.2, but it's negative because it's 27.8 minus 100, so negative 72.2 degrees Celsius. And now we know everything except for one variable, which means we are ready to solve. So I got negative MC delta T for the hot side has to equal positive MC delta T for the cold side. And I like to rearrange my letters first before plugging numbers in. I think it's neater and it takes less time to write everything out. So this is the thing I'm solving for. I'm trying to find the specific heat of my hot metal. So I need my equation to say C of my hot stuff equals everything else. Well, I don't need to move anything over here around. This MCAT stays the same. So the MCAT of my cold stuff stays the same. So this is all for the cold stuff. But I do need to get M and delta T of the hot side over here with MC delta T of the cold stuff. So I'm going to move the negative M delta T over to the other side by dividing. negative M delta T. From here, I can plug everything in. So M of my cold was 100 grams. C of my cold, or my water, is 4.18. And the change in temp that the water had was 4.1 degrees Celsius. And I put that all over. Be very careful not to forget that negative sign. Negative times the mass of my hot, 59.047 grams, and then times delta T of my hot, which was negative 72.2 degrees Celsius. So when I work all that out, and be very careful about your signs and make sure in your calculator, you know that that's supposed to go on the denominator. So make sure you give your calculator parentheses so it knows you want all that in the bottom. My calculator comes up with about 0.38, give or take some rounding issues. Let's check our canceling of units. So I have a gram on top. I can cancel that. I have 2 other grams. I have one here in the denominator and I have one there in the denominator. It doesn't matter which one you use this gram to cancel by. I'm going to cancel this one. I have a degree C on top and I have 2 other degree C's. I got one there and one there. Again, doesn't matter. They still cancel. One on the top cancels one on the bottom. So everything that's left, I got a J on top, a degree C on bottom, and a G on bottom. So that's what's remaining for this unit. And then if this question went further on to say, identify this material, since we solve for specific heat, and specific heat is a constant for the substance itself, I could just pull up a chart and I find that specific heat on here, and I find that brass has a specific heat of 0.380. And so this substance described here, this metal, must have been brass because that matches my specific heat. So that is how you solve a negative Q equals positive Q question. If you have questions, we will certainly talk about it next time I see you. Please work this one out and I will be checking that.